Okay, this is part 2A4C3M1b7c8e13cc. 13c3, sorry. Line 22f1fa19c3m1b7c8e13c3. I hope these numbers get shorter again. I keep adding to them because there's different keywords that all come together, so I keep adding letters and numbers to put those little things together, and I should have done a better system in this. Sorry about that. Atomic gases, magnetic, optical lattice, 5G Wow Seti. Our alien radio signals there. This is about keyword research for the core of the UFO spaceship. It's the structure, dimensions, rotation, math equations that you'll use for it. December 7th, 2012. Today's January 3rd, 2013. Sorry. The keywords to research from the data from the previous video, this is going back about 20 videos or so, is line 22f1fa19c3m1b7c8e13a quantum transport nanodevices UFO 5G Wow Seti. January 2nd, 2013, the most previous video before this one was line 22f1fa19c3m1b7c8e13c2 Quantum Hall Boltzman Quasiparticles UFO 5G Wow Seti. Chiral Luttinger. This is a quote from a blog. Realizing Luttinger liquids in trapped ultra-cold atomic Fermi gases using 2D optical lattices. Used in taxes, and there's the link there. Abstract. Okay, in this proceeding, we address the possibility of studying one-dimensional physics experimentally using optical lattices. These are periodic potentials created by laser fields in clouds of ultra-cold dilute atomic systems. We concentrate on the case of Fermi isotopes and study Luttinger liquid physics. In particular, we compare different regimes of spin coherence. We will argue that these systems are experimentally very attractive thanks to high degree of tunability and control, thus constituting an ideal laboratory for realizing model strongly correlated systems. So the keywords are optical lattice, Luttinger liquid, and noise correlations. Here's a schematic sketch of a 3D cigar-shaped cloud upper and the array of 1D tubes lower formed by a superimposed 2D optical lattice potential. This is a phase diagram of a 1D ultra-cold atomic Fermi gas. The dashed curve is a crossover line between the two regimes. There's the equation. Is the total density, and A3D is the 3D S-wave scattering length between different spices of atoms. I don't know if it's spices or species. I don't know. www.sciencedirect.com. Okay, and here is a band of zinc-blende semiconductor by considering a Luttinger nd.edu. Okay, looks interesting. Looks like some sort of magnet with some sort of force there. The quote diagrams are from the blog. We investigate a phi microdisc illustrated in the above figure. In this state, due to the competition between the exchange interaction and the shape's asymmetry, the magnetization lies in the plane of the microdisc except near the center, where the local magnetization is forced to point out of the plane to form a magnetic vortex. See? The diameter of the core RC to which the non-zero perpendicular magnetization is confined extends only over about 60 nm. In the figure below, we show the absorption coefficient for these three distances d between the microdisc and the QW. D equals 5 nm, 10 nm, and 15 nm. The energy of the photon is measured relative to the energy of the main absorption peak in the QW in the absence of a micromagnet. Vertical bars represent the optical oscillator strength of the transistors, and numbers nm show that the corresponding line is a transition between the nth electron state and the mth hole state. So from left to right, the charge texture for spin up states, charge texture for spin down states, note the smaller scale, and total spin charge texture, or arrows indicate the direction and relative magnitude of the local spin in the texture. There's your calculations there. The DMS SC distance is Z equals 10 nm, and an effective mass M equals 0.5 ME, and a moderate GEFF equals 500 for the DMS charge carriers, and that's from www.nd.edu. Okay. Our keyword search continues in the next video. Thanks for watching.